Hi, and welcome to my channel, Jabber Time, where I do math videos for all levels, from algebra to calculus and differential equations, simplified with examples. I'm also adding videos on apps and programs to help students and teachers alike, enhancing the learning and teaching online. If you're new here, welcome, and consider subscribing and hit that like button so that I know that you enjoyed this video. And also let me know in the comments below if you have any questions. I do upload a video or two every week, and I'm so excited about converting all my math notes from teaching over 25 years into simplified YouTube videos with examples. Once again, thank you for being here and hope to see you again and again. Alright, let's get into it. Hi, this is my third video for limits part 3 for calculus 1. We're gonna talk about a few things. Some of them are like end behavior, vertical asymptotes. I'm gonna add to it the horizontal asymptote and the slant asymptote. First video was 41 minutes, and I think 41 minutes is a lot for a video. So if you feel like I'm going a little bit fast, because I don't want to make it like an hour or 40 minutes or 45 minutes. So just stick with me, and I'll just go a little bit fast in some slides. If you need to stop me and pause the video, it's so simple. Just hit the space bar, that will stop it. Hit the space bar again, that will continue. So if you want to slow down on one page and write some notes, do that. Limits at infinity. We're going to talk about end behavior, and I'll start with simple math functions like x to the third, x to the fourth, x to the second, and so on, which we all are familiar with. So I'll just go a little bit fast here on these ones. When n is odd, x to the power n, as x approaches infinity, is just going to take off. And when n is odd also, when you go to the left, it's going to go down. What we say, odd functions, if you remember, we kind of like call them this way. From one side they go up, from the other side they go down. Any cubic function, any odd exponent polynomial, towards the end, that's how they act. Either this way or this way, which is kind of like, sometimes I call it like the moves or the Jabber moves. Alright? On the other hand, when it's x is to the second or x to the fourth, it's always like this. So here's kind of like to get used to me if you're new here. If it's even, it just walks this way, and if it's odd, it walks this way. So in other words, if you see somebody walking down the street like this way, what do you call it? You call it odd. And if you see somebody walking this way, what do you call it? An even function. Hopefully that will help. Even, odd. Even, odd. Alright? Even, sometimes even. Same side, if you have a minus up front, it's gonna flip it upside down. So keep those in mind. So when n is even, both going to the left and going to the right all the way, it's always gonna go to infinity. We're not putting minus here, so we should be fine. Let me support that with some graphs. This is x to the third, this is x to the fifth, and this is x to the seventh. I tried to align them for you. This way you could see that the only difference is like how fast they grow. That's pretty much the same. As x goes to infinity, goes to infinity. As x goes to negative infinity, the graph takes you down to negative infinity. Similar here, similar here. I'm not going to read this, and I'm trying to, as I said, I don't want to spend the time just reading all the details and make the video 1 hour. So just stay with me and understand why I speed up. Those are notes for you, not for me to read the whole thing. You could just stop by hitting the spacebar. Here's the even ones. As I said, x to the second, x to the fourth, and x to the sixth. It's like how fast it grows up. Let's look at this graph. If somebody asks you to graph this by hand, you should be able to do it. Let me support. 1 over x to the second is 1 over x to the second. It's not like the 1 over x, if you remember from previous video. So by adding 2, you could say like I have originally 1 over x to the second. Now I'm adding 2 to it. That means like 1 over x to the second is shifted up 2 units. The graph says it. What's the limit as x approaches negative infinity? As x approaches negative infinity, your values are approaching 2. You're getting close to this dashed line. We know this, but we're going to do steps. Here's the steps. Limit of the sum will be the sum of the limits. Those rules, I'm not writing them because I can't write everything and call it teaching. I'll just skip the basic things, and I'll just try my best to highlight and show you some examples. So that's how we apply the limits in steps. The first one is not going to go anywhere. 2 is going to stay 2. This is going to go to 0. So the answer is 2 plus 0, which is 2. And which shows that this line is your horizontal asymptote. So y equals 2 is our horizontal asymptote. Let's take another example that is also interesting. This example says 5 plus sine x over square root of x as x goes to infinity. We're going to take sine x on the side, and we're going to remind you a few things about sine x. We should all know enough about sine and cosine and how do they behave. Well, sine x has a minimum value of -1 and a maximum value of 1. It goes up and down to the max of 1 to the minimum of -1. It doesn't go beyond that range. So looking back at the problem, we have this package right here before I look at 5. So if I divide by square root of x, I'll have that. So let's divide this by square root of x. Of course, you have to divide all sides, right, middle, and left. And if you do this, it's not gonna flip. Inequalities flip if you divide by negative. But square root of x is not negative, that's one thing. Also, we're going to positive infinity, so there is no way I could worry about if this is going to be negative. Now, think with me. As x approaches infinity, what do you think happens to this right here? This grows and keeps growing and keeps growing. Same thing here. So as x approaches infinity, the first one is going to approach 0. And the last one is going to approach 0. Well, this lives between them. If this goes to 0, and this goes to 0, where do you think this one is going to go? Do you think it's going to go to 7? Well, it has to go to 0, and we know this. It's a common sense, but that's why I love math. Once you see it, it's just common sense. They call it the Squeeze Theorem, which we know this. It just adds up. I mean, it lives in between. This goes to 0, this goes to 0. Where are you going to go? You have to go with them to 0. So, what's the limit? Let's go back to the problem. The problem says limit of 5 plus sine x over square root of x. I'm just going to apply the limit to both terms. I'm going to walk in. And we just talked about this already. The Squeeze Theorem, that goes to 0. That 5 is going to stay 5. It's not going to go to 7 or 8 or 7-Eleven even. The store 7-Eleven. So it's going to stay 5. So the final answer is 5, and we have a horizontal asymptote at 5 because towards infinity you are approaching the level 5. So that should do it. To support that, if you have a graphing calculator, you could do it quick. Of course, there's other softwares and apps, but here's the graph. At 5, we're not defined. It's an open circle because, at the 5 as a level. When x is 0, it shows that the output should be 5, but we cannot be there. Why 0 is not allowed? Because of this. The denominator of this function right here is to the right of 0 for now. All right. You can't plug in negatives anyway with a square root. So, and because sine goes up and down, so it's going to increase and decrease. But eventually this is going to be too big. So this is going to be too small. So adding very, very, very small numbers to 5. So it's going to be 5. Even though it crosses it, this dashed line, but we still call it horizontal asymptote. Okay, another example. For this one, here's a new comment or concept. When you have a polynomial and you're applying the limit as x goes to positive negative infinity, always look at the leading term. Why is that? Let me write it down first, I'll show you. The leading term right here for this polynomial is a sub n x to the power n, and for our example is 3x to the 4. So let's keep this in mind. I want to just give you a quick comment. When you go to infinity, this and this and this won't even make a big difference compared to this guy. Trust me. I use common sense all the time, but I mean it has to. Let me show you with a simple example. Imagine if you have x to the power 5 plus 1x. When you plug in 100, you're going to have 100 to the power 5 plus 100. So that 100 doesn't make much difference compared to the 100 to the power 5. Okay? Imagine if you put a million, a billion to the power 5, then plus 1 billion. So that's the concept, which is, I said, common sense. So maybe that will help you memorize it. So let's get back to the problem and finish it. Limit this package right here. I'm skipping reading. It will be the leading coefficient only. And of course, you go positive or negative, doesn't make any difference. It's fourth power, and it's going to end up infinity. Another example. So what's going on here is the leading term what? Minus 2x to the third. Ignore the rest, trust me. That's going to go to negative infinity. Why is that? You have to look at two pieces now. X to the power third, or to the power 3, that's going to keep growing. So that's going to go to infinity. But I have a minus 2 up front. So it's like an infinity, a positive infinity, because we're going to positive infinity, times a negative 2, which is going to end up as a final answer to negative infinity. Okay, so there's two pieces. That's one way to say it. I think it's good enough for this, so let's take it the other way around, which means the negative. You're gonna now look at the leading term, and the leading term is minus 2x to the third. This is gonna stay negative. A negative 1000 to the power 3 is a negative number. Times negative 2, it's gonna stay positive. So that's gonna switch. Let me support that differently one more time. From your point of view, looking at the whiteboard, your x cubed looks like this. Minus x cubed is gonna take the minus 1, or the lower part, up, and the top part at the bottom. So instead of having it this way, you're gonna have it this way. Okay, that's called reflection about the x-axis. Whenever you have a minus up front, that's a reflection about the x-axis. What's on top has to go down, what's down has to go up. So that's what we have here, and hopefully it's clear. Let's talk about rational functions and in behavior. We have an example here, which is 3x plus 2 over x to the second minus 1. The idea here is to divide the top and bottom side, the numerator and the denominator, by x to the power n, where n is the degree of the polynomial in the denominator. Let's see, what do I mean by this. The degree, the highest power of the denominator comes from the term x to the second. So this is the highest one, We're going to see more examples. You're going to be seeing it so clear, and I have some more examples for you actually after a lecture. So go ahead and divide by x to the second here, by x to the second, by x to the second, by x to the second, and this is what we're going to do. So you divide the numerator and the denominator by x to the second. I'm not reading this, I'm showing it to you. So the answer is going to end up 0 over 1, which is 0. Now, if you go the other way around, x goes to negative infinity, same process. I'm not going to read that too. And we're going to go to 0. So towards infinity, I'm going right and left. I'm reaching 0. That means we have a horizontal asymptote at the x-axis, which is y equals 0. And I'm adding to it the vertical asymptotes. Where do you get the vertical asymptotes at x equals 1 and negative 1? Where they're coming from? They come from the zeros, if you remember my first video, of the denominator. Let's show you how. You see x to the second minus 1? It's right here, and it's in the denominator. So my function becomes 3x plus 2 over x minus 1 multiplied by x plus 1. Difference between two squares. The denominator here will be 0 if x equals 1 and if x equals negative 1. So we're not allowed to have 0. So we're saying we cannot have x equals 1. Because if I have x equals 1, that will cause this factor to be 0. We don't want that. And we don't want to have x equals negative 1, because if we have it, that's going to force this factor to be 0. Zeros of the denominator that don't cancel as factors, we call them vertical asymptotes. Alright. Next example. Now I'm not writing the whole paragraph. I'm just saying look at x to the 4 and divide the numerator and the denominator by x to the 4, the highest degree. Let me go over this quick and I'll show you some notes so you could make a comment out of it. Dividing every term on top and bottom side by x to the 4th, we have this. Now, going to the left as x goes to negative infinity, same steps, same idea, it's going to be 4. Which means we have a horizontal asymptote at y equals 4. Before I jump to the second example, I want to say something quick. You see this right here, that's x to the 4 and this is x to the 4. Whenever we have the same level, the same power of top and bottom side, the leading terms, what counts? Everything else goes away. Take it and look at the leading terms, divide them, look at the leading coefficients. This is the leading coefficient 40 and this is the leading coefficient 10. Yeah, that's your answer. 40 over 10, which is 4, without all these steps. So because it's the same power, take it from the leading coefficients. Next, divide by x. I'm darkening it for you so you can see it, guys. Save you some time. This is gonna go to infinity. That's gonna be just a constant. That's a 0, that's a 0, that's a 2. X to the third divided by x. We're dividing by x. It's gonna be x to the second. This is gonna grow. Imagine if you go like something close to infinity, minus 2 plus 0 over 2 plus 0. It's just gonna be infinity. Those don't count. And your final answer will be infinity. Top part is bigger, higher degree. It's gonna take off. So keep that in mind as a comment. Going towards negative infinity is gonna be the same process. So I'm gonna skip the steps and give you the answer. Alright, that's going to be ending x to the second, which is x to the third over x. So it's not going to make a difference when you say negative infinity. That's still going to be a negative big number squared. It's going to end up positive. That's why. So we have here, as you could see, higher on top it's gonna take off, so we don't have a horizontal asymptote. And if you factor the denominator or take 2 out and solve for the 0 of the denominator, you're gonna end up at x equals -2. You have a vertical asymptote. To support that vertical asymptote, I'll add this as a comment. That's the denominator 2x plus 4. You could set it equal to 0, subtract 4, divide by 2, and since the domain is all real numbers except -2, because we can't have -2, that's where a vertical asymptote happens. That's our domain. Here's a summary of what I just mentioned, and if you like it and you want to stick to it for a few more seconds, just hit the space bar and you'll be fine. That's rational functions, how they look like in general. A polynomial p of x over a polynomial of q of x, and we are concerned mainly about the leading terms and the leading coefficients. If m and n are the same, like 5 and 5, these don't count towards the end, so towards infinity you're looking at the same power, like 7x to the power 5 over 2x to the power 5. That's gonna take you to 7 over 2.
I found this on the web.
Sorry, my smartwatch. So anyway, m is greater than n, so the higher one is gonna be bigger, so it's gonna take you up, which means no horizontal asymptote. Go back to this example and you'll see more details. When m is less than n, so the n is bigger, which means the denominator is gonna grow towards infinity. The graph is gonna take you down to 0. And you go back to this example to see it, and y equals 0, which is the horizontal asymptote. Hopefully that notes do help, and I'm connecting it to our examples. Next, what is a slant asymptote, which is actually a very interesting topic. You don't see it a lot, but it's worth seeing it. Let's look at this example. 2x to the second plus 6x minus 2 over x plus 1. We're going to divide by x, which is highlighted for you, and you know why. That's for today's lecture. Doing that and simplifying, I have the following. So we're going towards infinity. I know that we're going towards infinity because it's not the same level, so the higher one is on top. But does it go this way? This slant asymptote example actually tells you that it doesn't go this way. It goes up kind of like this, and it goes aligned with a line. Let's take a look. What do I mean? This is for the negative infinity. I'm gonna skip reading it, and here's the long division. You know how to do long division of polynomials. Hopefully you'll understand that, and I'm skipping reading the steps. Now here's how we rewrite it. Dividing this polynomial by x plus 1, I get 2x plus 4 as an answer, and a remainder of -6 over x plus 1. We know how to do this because, for example, if I say divide 22 over 5, how many 5s in 22? Well, there's 4 of them, and there's a remainder of 2. So you could say that 22 over 5 is actually 4 5s and 2/5 as a remainder. Same concept right here. But that's interesting. And I keep saying that, I say it more than once. Take a look. As x approaches either positive or negative infinity, as we are discussing right here and right here, this fraction, which came from the remainder concept, will go to 0. The denominator is going to grow, so the whole thing is going to go to 0. So if this goes to 0, as x goes to positive negative infinity, this is what stays with you only. That's going to go away. Your values, as you go towards infinity, will get closer and closer and closer and closer to 2x plus 4, to a line that has a slope of 2 and a y-intercept of 4. To support that, here's a graph. You see it? It's so clear. It increases, 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 and gets closer to this line, which is y equals 2x plus 4, and that's why they call it slant asymptotes. Next, in behavior of major functions or main functions that everybody should know in calculus, e to the x, e to the minus x, ln x, sine x, cosine x. Everybody knows e to the x, the exponential function. E to the minus x, it's the reflection about the y-axis. We tell students that whenever x is replaced with minus x, it's a reflection about the y-axis. And we call this one growth, we call this one decay. As x approaches infinity, you're going towards infinity. That's this right here. As x approaches negative infinity, your values approaches 0, which is right here. These ones I'm not going to read. I'll leave it for you. Now graphing e to the x right here and reflecting it not about the y-axis, about the line in blue in between, which is called y equals x, you will have the reflection as green. If this is called f of x, we call this one f inverse of x, the inverse function. It's a famous graph and known function called ln x, the natural logarithmic function. Now, to support that this is the inverse of this, take a look at 0, 1. Reflected will be 1, 0. You're kind of like saying your x is your y is your x, your domain is your range is your domain. Anyway, that's where the log or ln x comes from. It's a inverse of e to the x. It's already here. Domain is greater than x because it doesn't touch the y-axis from 0 to infinity, not including 0. As x goes to infinity, you're going to infinity right here, and x goes to 0 from the right, you're going down all the way. So as x approaches 0 from the right, you're going down to negative infinity. Those are just notes. Here's more notes about sine and cosine. I can't fit them all here. We know that sine goes up and down, up and down, up and down, but I have to stop graphing because it doesn't end. And here's cosine. They look somehow similar. One period takes you 2 pi, then you have to repeat yourself. It says the limit of sine x as x approaches infinity does not exist. And going all the way to the left also does not exist. The reason why, because sine goes up to 1, goes down to negative 1, goes up to 1, goes down to negative 1. So towards infinity, you don't know if you're going to be up or down because it just keeps going. What we say is the sine function oscillates between negative 1 and 1 as x approaches infinity. So it's not like making up its mind. It's like when we say the limit is 5, you're just like getting close to 5. That's called the limit. If this one goes up and down, there's no limit. Same way for cosine. More examples. This time I'm gonna go a little bit fast, but if you noticed from the previous video and video number 1, in the description I write pretty much everything I cover, because my videos, it's kind of hard to make it like a 5 minutes video unless if I cover in it one example. But I'm hoping that my videos are like more than just one example. If I say I'm gonna cover calculus 1 and I just keep going, you're gonna see the contents in the description. So on limits part 1, if you look at it, there is a lot. You could click on example or topic or average velocity and take you there. If you want to start again from the beginning of average velocity, you just click on it. I'm gonna do in the description right here again a timeline. So please look at it, and if you want to come back one day to more examples, which is starting from here, you will see it in the timeline. You just click on it. You don't have to watch the whole video. You could just have it as a reference. You could click on examples, you click on slant asymptote, you will see it. You click on vertical asymptote, whatever I write in the description with the timeline, please, I don't want to keep saying this over and over in the coming videos, but I'll just remind you of the description and the space bar forward, backward. Let me know in the comments below any ideas. I'm listening to you guys. I'm doing this for you. I'm staying pretty much the whole night working on these videos, and I just want to keep going. So I need your support, and I just feel so excited to convert my notes into simplified YouTube videos. So help me, support me, and comment below, and I'll get back to you for sure. Here's an example. We're going to divide by x to the second, and you know why. And if you take your time, this is how it looks like. This is gonna go to 0, this is gonna go to 0, and 4 is gonna stay, it's not gonna go anywhere else. Now, as you can see, I'm speaking slower, but you could go to these examples as quick practice anytime you want. One more. We're gonna divide by x to the third, and I gave you another comment. Same power, leading terms, leading coefficients, and you're done. But let's just take a look at the steps. We're gonna divide by x to the third, the largest power of x, appearing in the denominator. Those are the steps. That's how you simplify. Everything goes away. This goes to 0, this goes to 0, 0, 0, 0, as x grows to infinity. This is only what stays with you, which I told you earlier. Leading terms, ignore this. That's what your answer is, 14 over 21. Which simplifies to 2/3. And here's another example. We're gonna divide numerator and denominator by x. And you should know why by now. Steps. Simplified. That goes to 0. And that's gonna keep growing. That's it. Infinity plus 3 over 1 plus 0. So it's gonna be infinity. One more example. We're gonna divide this time by x to the second, or you could just see it, 6 over 3, which is 2. Let's just see the steps. That's how you divide by x to the second. That's how you simplify. Everything goes to 0 here except these two, and that comes from here. Keep that in mind. And that's the answer. Now, going to the negative infinity, same style, same. So I'm skipping the steps. So the line y equals 2 is a horizontal line, a horizontal asymptote, I mean. Okay, I made it less than 41 minutes. It's 32 minutes or about, or 33. And that should do it. Thank you very much for watching. If you're up to this moment on this video, that means a lot for me. Thank you for watching, and I hope that this video was helpful. Hit the like button if you do like it. Subscribe, and I do really appreciate it. Comment below, and I will pay attention to your comments, guys. I will. If you like this video, hit the bell icon to be notified when I upload new ones. Until next time, peace, Jabber time. Thank you very much for watching. Goodbye now.